the first speaker of this afternoon session is Eugene Chua from University of California, San Diego. He will be talking about do black hole evaporate? Please, Eugene, you have the floor.
All right. Thanks everyone for coming. So let's get started. I'll just start with a bit of a backdrop. So this is very much a work in progress. Still working on a paper for this. And so, any comments or any feedback, suggestions, any things you want to poke holes at, that'll be very helpful. But, just try not to destroy me in the process. But yeah, so that's basically what I will be talking about, do black holes evaporate? So let's go so let's talk a bit about the plan, so you have an idea where I'm going with whatever I'm saying. So I'll just start with a bit of background on energy and symmetries in GR. So that's the basic arena for this course here, GR. And given the content of the last few days, I don't think we'll spend too much time on the background here and Hawking radiation. I'll just go through them really quickly. And if any questions, you can feel free to ask. So more importantly, I'll probably focus more from the step from Hawking radiation to black hole evaporation, which is, ironically, usually the shortest step of this derivation. Typically, I'll go into the arguments in just a bit, but I'll just focus on that part and, show some common arguments made in favor of black hole evaporation from Hawking radiation. And then I'll sort of get into a naive dilemma, like a really simple, straightforward dilemma that comes out of this sort of argument. And of course, since it's naive, you might think, oh, there's some sophisticated way of getting by this dilemma. And then I'll sort of marshal the tools of quasi-stationarity and asymptotic flatness, two usual tools used to simplify and, idealize calculations for black holes. And I'll argue, that these tools, even though they work as approximations, they don't really, the arguments require them qua idealizations rather than qua approximations. And that would come into play in sort of weakening or softening the arguments for black hole evaporation. So just get to the background here. Like I said, arena is GR. So in the semi-classical regime, gravity is typically assumed classical, follow the rules of GR unless otherwise specified. So this includes to me the rules of conservation laws in GR, and that's what I'll be getting into. Right. So this fairly straightforward stuff. We all know there's a local conservation law along a world line typically available in GR. We use it to start deriving the Einstein field equation to begin with. The covariant derivative of the stress energy tensor vanishes. So that's fine, right? But the problem is that doesn't translate well to the global context. The global conservation law, or what sometimes is called the integral, I think Lam calls it integral conservation law. That requires space-time to have certain symmetries. It's not always guaranteed, right? And using those symmetries, we can then derive a conservation law for a space-time if the space-time has those symmetries. But if there are no symmetries, generally we'll say there's no meaningful conservation law that we can talk about in the global context. So converse of Noether's first theorem is a bit tricky. I'm not gonna get into that here, but I think Brown has a really good paper that's forthcoming. I think it's on arXiv. That's pretty good. It talks a bit of the history of the converse Noether's theorem. So that's something you can look at if you're interested. So for the symmetries required for specifically for global mass energy conservation, which will be the thing I'll be interested in thinking about today, we usually have require usually a global timeline killing vector field, where killing vector field is a vector field on space-time along which the metric vanishes, the Lie derivative of the metric vanishes, along that vector field. So it kind of captures the idea that the metric may be considered as time independent in that space-time. It doesn't change over time in that space-time in some sense. And for every killing vector field, there is a conserved quantity. This is, I think Mr. Thorne and Wheeler cites this theorem in their textbook in gravitation. And I'm just gonna move on from there. Right, so in our context, we're talking about black holes. So black holes do have global symmetries, right? But usually they are for stationary black holes. So static or stationary black holes that do not change over time. You can kind of see from the Schwarzschild and the Kerr matrix, right? At least in this, so the Schwarzschild coordinates and the Boyer-Lindquist coordinates, the coefficients are time independent. The m is a constant, right? That's usually that's the case. And if you want to make it not a constant, then that's not the Schwarzschild stationary metric or the Schwarzschild static metric. That's something else that looks like it, right? So this is usually the examples that people use to model black holes, the Schwarzschild metric and the Kerr metric. Right. So getting to the to Hawking radiation, let's take a look at some of the core claims of Hawking radiation. But we have done quite a lot of this. Way more qualified people have talked about this in the last few days. I'll just briefly whiz through it. Right. So for black holes, supposedly at late times, notably late times means state collapsing stars settle into a stationary state, and then you observe a Hawking radiation from this stationary black hole, corresponding to emission from a perfect black body at the Hawking temperature, which is here. And the usual procedure is you kind of take space-time, define a vacuum field at future infinity and past infinity, split them up, and then compare how they look like. And then you kind of after and before a collapse of a black hole, and then you compute and the differences and find the Hawking radiation arising from near the horizon. So some other core claims here. The firstly, like non-localizability, so that's a mouthful. Globality. So a property, Hawking radiation is a property of the entire horizon. It's a global thing. It comes from all of the black hole at once, right? The observer at spatial infinity, at future infinity, observes the radiation coming from the black hole. It's not localized to a point on the horizon. You can't say this is where Hawking radiation is coming from. It comes from the whole thing. So you need either a lot of time or a lot of space, so to speak, to really measure Hawking radiation coming from a black hole. Oh, is that a question? Yeah, Eric, your question?
Just to clarify, when you say it's a property of the entire horizon and comes from all the black hole at once, are you referring to the entire three-dimensional event horizon, or are you referring to the two-dimensional slice at a moment of time, so to speak?
I think I'm referring to the three-dimensional one, but correct me if I'm wrong there.
I think it's more correct to say that it can't be localized at a point at a moment. So,
okay.
It's really the two sphere at a moment that is the intersection of the three horizon with the time slice that at the point refers to.
Okay, right. So that's that's a way more precise way of putting it. Right, and secondly, the Hawking effect is observed as emitted from a stationary black hole, right? As we've said, is at late times after black hole has settled into a stationary state. Right, so this is so much for radiation, right, per se. And the step from Hawking radiation to evaporation is where things are a little more interesting, I think, because is usually not it's not so much a formal argument. Usually, it's like just a single step, right? And this is we need to think about evaporation because we need to consider back reaction of Hawking radiation on the black hole, right? At least that's how we think about it. So, what does the effect of Hawking radiation? What is the effect of the Hawking radiation on the black hole itself? So, as Wallace puts it here, the derivation of Hawking radiation itself doesn't establish that Hawking radiation is fully analogous to ordinary thermal radiation, because it doesn't say anything about whether the black hole decreases in mass and surface area per se, the radiation itself, because it's calculated in a stationary space-time. So given that there's no robust local definition of gravitational energy, it's kind of tied to the non-local notion of the non-local feature of Hawking radiation, as well as we can't understand total energy as a sum of local energies generally. We cannot appeal to a local conservation law, i.e. the divergence version, to sort of conclude that radiating black holes evaporate. So what do we do then, right? So Hawking's argument, typically, I think the one in 1975, he talks about how the positive energy flux out across the event horizon equivalently leads to a negative energy flux, right? So this implies some sort of conservation of mass energy at play here, right? And in 76, he makes it a little more explicit, right? The radiation carries away energy, so the black hole presumably will lose mass and eventually disappear. So again, there's some kind of conservation reasoning going on there. Wald says more explicitly in the 2001, I think, Living Review. So he talks about how conservation energy requires that an isolated black hole must lose mass in order to compensate for the energy radiated to infinity by the Hawking process. And Khalid just equates it to a Stefan Boltzmann type law, where the right side is just the power radiated by like a massive object, but he equates it to DMDT, which is equating the power loss outside to the loss in mass inside the black hole. And Carroll and Wallace talks about it differently, and I'll talk about this later as well. they talk about conserve energy, but not in the global, at least they specify what they are talking about when they're talking about conservation energy. So Carroll talks a bit about conserve ADM mass in asymptotically flat spacetime, and Wallace says the same, the symmetries of Minkowski spacetime at infinity, which is basically asymptotically flat spacetime, and the global conservation law we can get from there, and the ADM mass we can get from there, and then from there we can get our argument for evaporation. Right. So I think with these ingredients in play, we can sort of formulate a simple, like, naive dilemma, right? So there are two options, it seems to me, at least in first glance, right? You have a stationary black space-time, or could be modeling a black hole, where you have global time-like killing vector fields, global conservation law for energy. It's time independent, stationary or static, right? But this means it cannot evaporate because it's not changing in time. It's just there, right? Whereas the non-stationary space-time, right, it's generically no global time-like killing vector field, no global, and therefore no global conservation law for energy. But it is time dependent, so it's dynamical. It can evaporate, right? But it seems to me that black hole evaporation requires two things, some parts of each, right? You need a global time-like killing vector field, and or like some kind of global conservation law for energy, at least a non-local one. But you also need the process to be time dependent and dynamical. So there's a bit of a dilemma here, because if something is either stationary or non-stationary, then we cannot get properties of both out at the same time. And black hole evaporation seems to require that. If it's stationary, it doesn't change, so there's no evaporation going on there. If it's non-stationary, it can evaporate, but then we have no reason to think that it will evaporate to begin with. So that's really the dilemma that I'm constructing here, a really naive one. Right, so this one. Sorry, this is basically what I just said. The mass parameter is constant here, and on the other side, it is not constant, but why would we think that there will be evaporation to begin with? So the quasi-stationarity is used first by Hawking, I think, at least in response to this sort of problem, right? So he was aware in 1975 of this problem, and he intended quasi-stationarity to do the job of getting the best of both worlds. So quasi-stationarity is a claim that a black hole changing over time can be approximated by a sequence of stationary or static solutions, depending on whether black hole is rotating or not, and whether it's charged or not, and so on. Right? It's used everywhere, but it's not always explicit. Right? So the way Hawking used it here, the negative energy flux will cause the area of the event horizon to decrease, and so the black hole will not, in fact, be in a stationary state. So this is contrary to the derivation of Hawking radiation, where the black hole was assumed to be in a stationary state to begin with. But then he talks about it here. It's a reasonable approximation to describe the black hole by a sequence of stationary solutions, and to calculate the rate of emission, i.e., Hawking radiation in each stationary solution, if the rate of evolution of the black hole is slow enough, right? So it seems like we can sort of make this response a bit more concrete, at least in response to the dilemma. How do we resolve this problem of things either being stationary or non-stationary? So we can sort of think of it as this way. In the time-independent stationary solution, in one step of the process, there is global conservation of mass energy in that solution, and then we can derive Hawking radiation in this solution, and using conservation reasoning here, conclude that the mass energy of a black hole must decrease. So there's a negative energy flux there. But in this single solution, it's stationary, right? So change can't happen in this solution itself. So decrease must happen outside of the solution somehow. It applies to the actual time-dependent black hole being modeled by this quasi-stationary process. So since the black hole is non-stationary, evaporation can occur in this region. So how do we do that? There's no mechanism for changing the mass, right? So we just perturb it, we just change it kind of manually, basically. And we just say, well, it goes from one stationary state to the next stationary state. And we get a quasi-stationary process this way by iterating on this procedure, right? So this is an example of like a quasi-stationary process, right? There's no change, energy conservation, but somehow there's change that comes here, and then no change again, and then change, no change again. So, yeah. So it seems to me that it's not so clear cut that this is conceptually okay to do, right? And to sort of get clearer on the issue, this kind of reminded me immediately of I think I mentioned it, like Q&A with Eric before. Like it reminded me of quasi-static processes in classical thermodynamics, and some of the conceptual issues that arise there. So you can see like a classic quasi-static process, Carnot cycle. each point on this graph represents a time-independent state, or like, you know, a reversible state. Oh, sorry, equilibrium state that is on a reversible process, right? So they're time independent. They're equilibrium states. They don't, by definitions, they do not change with time, right? But thermodynamics frequently makes use of quasi-static or reversible processes consisting of sequences of these equilibrium states. So you can kind of see you can kind of see more clearly here, but, you know, like there's a like an analogy here, maybe even like a structural similarity between the two processes. They both kind of model things that really do change in time, really are time dependent, but using a process that consists solely in time independent states and systems. So, you know, we know that thermodynamic objects change. In fact, sometimes irreversibly over time. You know, a cup of coffee cools down, a mug of beer warms up, the egg fries and never unfries itself, and so on. So we have something similar here, and it seems like they both give you the best of both worlds, right? You can approximate a system with a quasi-static process such that, you know, at each point of time, we can treat it as effectively time independent. And so since it works in thermodynamics, maybe it'll work in black holes as well. So that's the thought here, right? But I like to think that the reverse is kind of true as well, that if it doesn't work in thermodynamics, we might be able to see why it might not work in black hole physics as well. So the caveat for quasi-staticity, as Norton kind of pointed out in his 2016 paper and elsewhere as well, in 2017 as well, talks about how it's literally an impossible process. The title of the paper was like quasi-static, I think it was reversible process is the impossible process or something, right? The equilibrium states are by definition states that do not change with time. But a process, quasi-static process is one which does generically change with time, over time. So that, you know, we have a state that at each state it doesn't change, but over time it changes. So there's a contradiction there. It's almost like a Zeno's arrow kind of argument going on there as well, right? So how do we do that? Obviously, we use the quasi-staticity in our thermodynamics. So we can't just say, you know, it doesn't work, let's just give up all of it. So the question is what parts work and what doesn't. So Norton proposed a schema for, I guess a schema is fine, for thinking about the difference between approximation and idealization. And we can, in this schema, we can see that a quasi-static process is idealization, which time-dependent systems approximate but never exactly get described by. And that's good because the process is an impossible process. It's not possible to realize a quasi-static process, literally speaking. So we have an approximation, which is broadly speaking, an inexact description of the target system, and idealization, which is a real fictitious system distinct from the target system, some of whose properties provide an inexact description of target system. Basically, the idealization is a thing that may not exist, but some of its properties can be found in approximating system. Whereas approximation just means you're being inexactly described by something like an idealization. So in a simple example here, a small falling unit mass can be modeled by something like this if you take expansion in the exponential term here, right? And, you know, if you assume that k is small, right, you can let then this thing will approximate, then this will approximate a system, a real system with small friction coefficient k, right? But only in an idealized case, when k literally vanishes, do we get a limit system, which is where the velocity of a falling unit mass is literally gt, right? And it might be possibly fictitious in cases where friction never goes to zero, right? You know, in the real world, maybe friction never exactly goes to zero. It might be vanishingly small, but never zero. So it's an easy case here. Since zero friction cases do exist, right, we can kind of sometimes promote approximation to idealization if we have some kind of vacuum chamber, for example. But other problem cases suggest that we cannot always promote an approximation to an idealization. So I think Norton gives an example of a sphere with I think a tree sphere with like some r parameter radius, and, you know, he says that, well, we can take r to be larger and larger and larger, but we cannot take r to be literally infinite. That's not a possible sphere. It's not a sphere anymore if the r is just infinite. Like, we can get to arbitrarily large r, but not an infinite r. So in the same vein, quasi-staticity is an idealization in that sense, right? As he puts it here, the limit approached by the processes themselves is not a process at all. Right? It's a static set of states in equilibrium that does not complete the limit property of completing the change. So we can assume that in a quasi-static system, or a system modeled by a quasi-static process, there are driving forces, net driving forces that causes the change. By, for example, you perturb the system, poke the system a bit, slowly shake it a bit. Right, those are like driving forces we can move to near zero, and that drives the change of the thermodynamic system. But it's also clear that that we can like literally have, if we don't do anything to the system, it doesn't change basically, right? So, but that's exactly what equilibrium means. We're not doing anything to it; it just stays in equilibrium. So, it can model time-dependent systems approximately, which means inexactly, if the time-dependent processes come arbitrarily close to quasi-static processes by having vanishingly small driving forces. But it never realizes the idealization of quasi-static processes. So now we can come to like a brief distinction between essential and inessential idealization. Right? So sometimes the limit properties and idealization is necessary for something, for an argument or a prediction. Right? And it's a problem when the limit system doesn't exist. Whereas most of the time, limit properties are not necessary, and you can make a prediction or an argument in terms of the underlying system approximating idealization, or you understand that it as an approximation instead. So for quasi-static idealization, it's not essential that it's like quasi-static in the sense that it's not essential that it must be equilibrium all the time, right? And also like dynamically changing. So the time dependence and independence are not both needed to model a system. For large systems, we can assume that the driving forces are small again, but we can explain the behavior of the underlying system without the idealization that the system is both time dependent and independent at the same time. That's not essential to the argument. And another example that has been discussed quite a bit in the last decade or so, or even more, I guess 20 years by now, calendar, Butterfield, Mino and calendar, Patricia, the idealization of a system exactly at a thermodynamic limit is also not essential to the understanding of phase transitions. We can see how phase transitions arises before the limit, so to speak, as the number of systems go to infinity, but not at infinity, just like arbitrarily large finite numbers. We can get a prediction that works. So the phenomenon of phase transitions does not require the actual existence of a system with infinite number of particles. Again, that's great because there are no such systems to our knowledge. Right? So system displays a phase transition-like behavior before the limit. And similarly, quasi-stationarity, so going back to the original question, quasi-stationarity is also an idealization. Stationary states are those that do not change in time by definition. The metrics are by definition time independent. Quasi-stationary process is one which does change over time in the time-like direction. So contradiction is inherent in this concept, and it's a fictitious process as a result that only inexactly describes actual systems. So now the question, returning to black hole evaporation, is quasi-stationarity essential to the argument for black hole evaporation? Does it, notably the argument relying on conservation of energy, does it require a property that exists only in the idealization? And it seems to me that it is essential to arguments for black hole evaporation because we need a global conservation law to motivate a loss in mass to begin with, and we need stationarity for those for that property. But we also need dynamics to model actual evaporation, and for that we need non-stationarity. So some people can propose, what if we can find something that looks like killing fields, like they are approximate, but they are not exactly killing fields. And underlying space-time can be thought to have something like this sort of approximate killing fields, and socially something in the underlying space-time exists before the limit, just like the other cases. And so in that case, stationarity is not an essential property of the quasi-stationary process, right? So I think one problem that Eric mentioned before, I think on Monday, right? It seems like there's no background structure against which we compare deviations of any vector field from the killing field. Right? In the Newtonian space-time, we have a uniquely sort of maximally symmetric background space-time against which we may compare deviations. But procedures that are out there, at least to my knowledge, it'd be helpful if you can provide me with more. Procedures typically compare their almost killing vectors not with an ideal sort of killing structure, but with other non-killing structures. For example, like a conformal killing field is the closest thing, I guess, to a killing field. But they also compare with other sort of proposals for killing fields, like almost killing equations and so on. So it's kind of like they're comparing other proposals, but they're not comparing with, it's not clear like they're comparing with the killing vector field itself. So it's not clear what closest means. This goes on to the second problem, that there's no clear metric of closeness, it's only that it is the closest. Right? It's not quite the same, right? We can say that something is closest to me without telling me how close it is to me, right? So for example, Matzner's procedure, it guarantees the produced vector is the closest by choice, right? You choose the lowest eigenvector and you say, look, the vector with the lowest eigenvalue, and you pick that as the produced vector from this eigen problem, I guess. And you use that and just say that is the most closest thing we get, but you're not telling me how close it is. So Cook and Wheating has something similar as well. They have this, I guess, like a covariant term here, like a inner product term, but they never provide a clear indication of this term. It's just as close as zero as possible, but not exactly how close. They don't tell us how close it is. So Lovelace as well, they show closeness of the approximate killing vector to a deformed rotation vector in curve space, but never compares this to the killing vector. So again, how close is it to symmetry? I don't know, right? So again, also there's another problem, which is that the procedure guarantees some killing vector field, almost killing field, but not a time-like one. So you're not guaranteed to get a time-like killing vector field for this procedure. So that suggests, it's not it's not generally true that any cyclic spacetime when approximate gets a time-like vector field. And there's also a problem with degeneracy. So solutions typically are, I think, degenerate. It's possible that it's degenerate and also may not be unique. And also, I think that I mentioned here, but didn't really put in here. There's no canonical normalization for the vector field produced, and you need that to get to hook up to the empirical predictions for any spacetime. And another problem, I think just a list of problems here, and each of them can be investigated in much more detail than I'm doing here. Finally, I guess some approaches require strong assumptions. Compact spacetimes, for example, or existence of asymptotically flat region. Feng et al. Shows that the Bona et al. Proposal for an almost killing equation leads to an unbounded Hamiltonian runaway instability and Gauss degrees of freedom, except in almost all cases except one. But that case requires, again, asymptotic freedom, asymptotic flatness and divergence-free condition. So we can kind of see, to sum up, I guess, it seems like the problem with approximate killing vector field, right? The idea is not clear enough for me to say whether it works as a resolving the problem of inessential idealization for quasi-stationarity. And if this not works out, if there's no clear answer to this, then it seems like we have no way of even saying what it means for a killing vector field to be approximately killing. I guess a vector field to be approximately killing. And that means we cannot even put the argument into words to talk about the conservation law and therefore to talk about black hole vibration. So another solution that has been proposed.
Sorry, Eugene, you have 5 minutes.
Yeah, that's fine. It's the last part. So another solution typically is asymptotic flatness. We might agree that quasi-stationarity is busted. As an idealization, we don't need it. But we don't need it because we can use asymptotic flatness instead to give us the conservation law, as well as Carol mentioned just now. So we use the asymptotic flat property of stationary spacetime, but not the stationary property of stationary spacetime, essentially. And that means we can get around the argument that I provided just now. Right. So the intuitive idea is that the metric approaches Euclidean metric sufficiently rapidly at infinity. So something like this. At the limit of spatial infinity, spacetime is maximally symmetric. And at this limit, you can take the spacetime to possess a time-like killing field, asymptotic time-like killing field, and then exploit this symmetry instead of the stationary one to get a global conservation law for mass energy. And this is fine because each stationary solution is asymptotically flat by construction. Also, it seems. Right, so ADM mass is defined globally on spacetime using only the structures at spatial infinity. And it can be derived using the asymptotic killing structure I mentioned here, as the road shows. And then you can use this law instead of the law provided by stationarity to motivate the argument for black hole evaporation. But it seems to me there's a bit of a redux here, right? So typically, asymptotic flat spacetimes they are stationary, but the non-stationary one, it seems like, as if Dewar is right, Robinson-Troutman class of metrics are the general class of non-stationary asymptotically flat spacetime. They are marked by naked singularities, and that might be a problem that we want to deal with, or it might be fine as well if you think that naked singularities are fine. But that's just a prima facie problem that we have. But you can still use quasi-stationary here, coupled with stationarity instead, so that we avoid this problem. So maybe this is not the problem here. But the problem is that asymptotic flatness is also an idealization. Right? Literally, it's false. Our universe is not asymptotically flat; it's asymptotically de Sitter. And there's no notion of spatial infinity available in the de Sitter spacetime. I think Britton mentions this in his paper as well. So results using asymptotic flatness does not even apply to our universe if we take asymptotic flatness literally speaking. So again, the answer, maybe you can use it as an approximation, and that's probably the answer that most people have in mind, right? You can use it to approximate certain systems. For example, Wall says this. So the question is, does black hole evaporation essentially require the idealization of asymptotic flatness, or just something inexactly close to it? In other words, can we safely sail to spatial infinity in some sense in the approximation? How far does it take for the asymptotically flat metric to break down for a realistic system? And again, Duo has a few arguments for this, and mostly I'm just mentioning them and then developing them in a bit more detail. It breaks down in the simplest case if Ashtekar is right, Ashtekar at all, right? That they're modeling isolated stars radiating in the asymptotically de Sitter spacetime, i.e., our spacetime, with a positive cosmological constant. However, they observe that if you just let cosmological constant go like larger than 0, typically there won't be an existence of even if you're treating this spacetime as like a short-short de Sitter spacetime as an approximation. Typically, this model will not admit even asymptotic flatness at infinity, right? And if we just pretend that the cosmological constant goes to 0 within this spacetime, so that we can get to asymptotic flatness, it leads to discontinuity in the energy term. So we cannot pretend to turn off the cosmological constant. And demanding that actually leads to some kind of arrested development where the gravitational waves being emitted they're just not possible. The dynamics basically shut off when you let lambda go to 0 in this case. So in other words, in Ashlekar's words, while it works for first post-Newtonian system approximation, some of the subtleties associated with a non-zero lambda could be important for future detection that could receive signals from beyond the cosmological radius, and important for analysis of long wavelength radiation produced by black holes. And also there's some empirical differences for lambda not equal to 0. There's a novel observationally viable limit according to Ashtekar. On non-rotating black holes, there's a limit based on the lambda constant. And this has been corroborated by some numerical simulations and first proposed by Shibata et al. I think in 1994. So it seems like we don't get smooth sailing to spatial infinity even as an approximation. The approximation kind of breaks down at large but finite distances, cosmological distances, when the first post-Newtonian near-field approximation breaks down. The near-field theory breaks down as R goes to infinity. And it's induced what it cannot incorporate non-incoming radiation boundary conditions. So the upshot, it seems to me that asymptotically flat spacetimes are good approximations to some large R, but the limit property of exact flatness and R equals infinity never obtains because we never quite get there. The limiting procedure breaks down for realistic black holes. So defining a conserved ADM quantity requires a limit property which never exists. And this means that we cannot use this asymptotic flatness as a way to define an energy term for predicting black hole evaporation for realistic black holes. And trying to come up with something called approximate asymptotic King structure leads probably back to the same problems that I mentioned earlier before. And it seems like the idealization of asymptotic flatness is essential to defining a global conservation of mass energy. Right? So it's kind of like an ideal posit in a sense. And we have tried to use. I think I'm just going to conclude here, right? So what I've argued is that the argument for black hole evaporation to Hawking from Hawking radiation to black hole evaporation requires some global notion of conservation of mass energy. Leads to like a naive dilemma. It seems like a super simple dilemma, but there are some sophisticated ways of trying to deal with it. But I try to argue that both do not avoid the dilemma because they're both just essential idealizations for the black hole evaporation argument, but idealizations do not obtain. So some future things to consider, you could define a quasi-local term like a Brown-York tensor, but it seems like for those terms to be conserved on like the 2 surface, it also requires some killing structure in that 2 surface. It's not clear that that always exists as well. And killing horizons are also used to define black hole, define Hawking radiation. That requires killing structure as well, which may not always exist. And finally, it'll be more fun to investigate more on approximate killing fields as well, I think. But I guess with that, let me just wrap up and thank you all for your time here. And sorry I went a bit over time. Yeah. Right.
Thanks, Eugene. Okay. Other questions? Katie, please.
Hiya, thank you. It was really interesting. A lot of content But the question I had for you was really this connection to the thermodynamics case. So it seems like at first I thought, well, hang on a second, it seems quite disanalogous, because I think it's something that Norton doesn't really emphasize, but the kind of crucial feature for understanding quasi-static processes in thermodynamics is that you need some kind of external, you've got some kind of external parameter that's changing. So like this kind of the system being part of a larger system is always kind of a crucial part of thinking about thermodynamic processes. And obviously in the case of you considering the whole universe, that seemed kind of disanalogous. But then it seemed as the talk went on, the crucial thing for you wasn't so much the connection between quasi-stationarity and quasi-static processes and thermodynamics, but rather this like essential versus inessential account of idealization. So I guess I wanted to just like, just clarify exactly, it's not that the relation to quasi-static processes is key, but rather this thing that Norton himself draws out of that, which is this idea about idealizations.
Right. Yeah, I think that's why I started thinking about quasi-static processes in relation to quasi-stationarity, because I thought they look kind of similar. But you're right, obviously, like, you know, they're two different theories, and I mean, unless you think they're both thermodynamics, really, right? And then then there might be some stronger analogies there. But I agree that, you know, they're not completely analogous. But I thought the interesting thing was that both of them had the same issues, which is that you know, some parts of the idealization was needed and some others were not needed, and that's where the investigation began.
I guess this kind of essential versus inessential idealization is always going to, like, using that as a crucial feature for understanding idealizations is always going to be open to the problem that some people might, you know, it's open to the kind of interpretation, like whether you think something's really important or not will depend on how you conceive of the problem. So I guess it kind of but anyway, that's just a thought.
Yeah, right. But I guess I feel like it seems like essential is quite strong here, because you like literally need the structure to even talk about, for example, ADM integral, because it's defined at r equals infinity, like r at infinity. But you need that structure. So I feel like anyone who tries to compute it will need it. So I feel like it's essential in a fairly neutral sense. Yeah.
Okay. Other questions?
All right.
I just wanted to make sure that no students or younger researchers had questions first, but yeah, okay. If no one does, I'll go ahead. So I have a few remarks and a question. Just a clarificatory remark is that in the Ashtekar 2016, the issue of radiation has nothing. The radiation has nothing to do with the issues that you're talking about. It's just that if you have lambda equals 0, you never have asymptotic flatness. Doesn't matter if there's radiation or not. So the radiation was a little bit of a red herring there. I was a little confused by how the first half of the talk related to the second half, the part where you're talking about global killing fields and global conservation laws, because as you rightly noted in the second half of the talk, to have conservation laws at space like infinity, to have a conserved ADM mass, you don't need a global time-like killing field. You don't even need to specify an asymptotic time-like killing field. If you have a strongly predictive asymptotically flat time, I can't speak. Strongly predictive asymptotically flat space-time, which every unless you have naked singularities, you basically will have for anything like a radiating black hole, you automatically get conserved ADM mass. So I didn't understand. And if you have a global time-like killing field, you're not necessarily in a space-time that has an asymptotic completion. So there just seems to be no necessary relation whatsoever between the issue of having a global time-like killing field and having the asymptotic conservation, and it's really the asymptotic conservation that you want and need for the black hole evaporation phase. And there's one further aspect. I guess I'm sounding pretty critical here. So I guess I really should have started by saying I thought you did a really excellent job. The discussion of the approximate symmetries was fantastic. I thought that was really great. That's a problem that really deserves to have a lot more attention paid to it. And you brought up like really important issues about it. And I thought that the treatment in the second half of the with the asymptotic symmetry stuff, I thought that was that was really well done. And again, you really put your finger on a lot of important issues. I just didn't really quite understand how the first part related to the second part. And then there's one thing I felt like you left out in the second part, which is the issue isn't just that you need a changing ADM mass. You need to relate the changes in the ADM mass to the fluxes of energy at functional infinity. Exactly like the kind of thing, here, I pulled up the reference for this. Exactly what Magnin and Ashtekar did back in '79 when they proved that for general, I'll put it in the chat, for general gravitational radiating spacetimes that are asymptotically flat, you get exactly the relation you want, that the change in the ADM mass is equal to essentially the integral of the Bondi-News function on functional infinity, which that says that that the change in ADM mass is exactly equal to the energy flux at functional infinity. So energy being lost to gravitational radiation. So there's really a conservation law, and you want the same thing for Hawking radiation. You don't just want to say the ADM mass is changing. You want to say the ADM mass is changing in exact so as to exactly be compensated by the flux of the Hawking radiation at functional infinity. And there are approximate arguments. To the best of my knowledge, there's no exact theorem that shows anything like that. There are approximate arguments. So this is exactly, grist-fear mill. But okay, I'll stop there. You can see what you have to say about that.
Yeah, I think that was very helpful. Thanks a lot. And look at the links as well. Yeah, I think I think the structure of the talk mirrored more the structure of how I came about this idea rather than as a fully complete product. So I came across it while thinking about quasi-stationarity, and I thought, hey, that seems like the most obvious way to define conservation. Right? I mean, you have a global global time-like killing field, then you're done, right? You have the conservation there. So I thought that could be like a straightforward thing to get thinking about. And obviously it doesn't. I mean, I tried to argue that it doesn't really work out, but then it got me thinking about the idealization stuff, and then that got me to asymptotic flatness. But you're right. I guess asymptotic flatness is the highlight, so to speak. Maybe I could like shorten the quasi-stationary stuff, expand the ADM stuff, or the asymptotic flatness stuff. But I do think they're kind of related because they're both ways of trying to get some kind of conservation law out, from which you can get argument for operation, right? So if you have if the argument from quasi-stationarity works, then you might not need asymptotic flatness. You can just use the stationarity and do the work for you. At least that's how I was thinking about it. Yeah. Yeah, and for the Ashtekar, I need to think about it. That seems like good good evidence I can rely on for my argument. Really. Yeah. So thanks a lot.